first speaker today is Suvrat, Raju, who will be continuing his lectures on the information paradox.
Okay, so thank you very much. So before I start, let me just remind you of what we did last time. So last time we discussed what sometimes I would call the naive information paradox. And the naive information paradox is the statement that if you do a leading order calculation in the black hole, collapsing black hole geometry, it looks like the radiation that you get out at the end is thermal and seems to depend only on some macroscopic parameters of the black hole and not on all the microscopic information that went in. Now, if this was really correct, this would be a paradox, but as we discussed last time, just taken on face value, this by itself is not a paradox. It's just a statement of the thermalization of pure states, and it's a statement that most pure states, in fact, look very close, and we quantified how close. They look exponentially close to mixed states. So if you wanted to create a paradox in this way, by extending this calculation, you would have to work much harder, go much beyond leading order, and in fact go also beyond perturbation theory in order to create a paradox this way. So this is what we talked about last time, and what I'll talk about today is refinements of the information paradox, and how it looks like you can get a paradox at order 1, and then what I'll talk about in the third lecture are proposed resolutions to that. But before I start that, are there any questions from last time that we can address now? Okay, so let me start by talking about some refinements of the information paradox. In fact, I should mention that this program was started with Sameer's work about 6 or 7 years ago, and I know Sameer already talked about this briefly in his lectures. So I'm for the first some time, I'll spend some time just reviewing Sameer's work from 2009 on extending the Hawking paradox to what's called the strong subadditivity paradox. So the strong subadditivity paradox was also later popularized in the work of AMPS, and there was a lot of discussion about the so-called firewall, but really all of that was first done by Sameer, and I'll point out what that work is. So I'm going to spend the first 15 or 20 minutes first just describing how you can refine the Hawking paradox to turn it into a paradox where it looks like you require corrections at order 1, and then I'll give you some proposed resolutions to that. So I want to describe, in fact, two refinements of the paradox. One of them is called the strong subadditivity paradox, which I already mentioned. The second one is actually an older paradox, but it's something which is very closely related to strong subadditivity, and that's called the cloning paradox. And this is something that was first discussed by Susskind, Thorlacius, Uglum, and others about 20 years ago. And I'll try and point out how both of these paradoxes give you a sharper version of the information paradox, and how they're also closely related to each other. And one thing that's distinctive about both of these versions of the information paradox is that they make reference to the black hole interior. And this is a general slogan. If you really want to set up a paradox with Hawking radiation, you have to make reference to the interior of the black hole. If you just look at the outside of the black hole, you don't really get too much of a paradox. That's because, you can always use an argument that pure states look close to mixed states, as we discussed last time, and resolve that paradox. But it's when you make reference to the interior of the black hole that you start sharpening the paradox. So both of these paradoxes will have this property. So let me start by reviewing the first paradox. So the first paradox goes as follows. And once again, I'm going to make reference multiple times to the notion of entanglement entropy, which we discussed last time. And I'll make reference to it once again. So imagine you have a horizon of a black hole. The horizon of a black hole is actually a light ray. Okay, so you should remember the horizon of a black hole is a 45-degree line, and it's some light ray. Now, we want to divide the black hole space-time into some number of regions. One of them is a region which is just outside the black hole, and this region we'll call B, okay? And this is between green and red. And that's the region just outside the black hole. And there's a region just inside the black hole that I'll call region C. A, which this is the region A. Okay. So is this figured here? So what we have is the horizon. The horizon lives at r equal to 2n. We have some region outside the horizon. This is a constant r surface. And that region, the region between the horizon and this constant r surface is what we'll call region B. Okay. This is actually a hyperbola, but I'm not interested in all the hyperbolas, so I've drawn some small part of it. And then there's a region behind the black hole, which is at some region r equal to rc. The boundary of that is r equal to rc, where rc is smaller than 2n. And the region between the blue and the green is C, and the region between this and the red is B, and everything outside the red is region A. Okay. So it's not very imaginative notation, but I've written it here so you keep track of it. Okay?
Any assumption on what the size of these things could be?
Well, we won't need a very strong assumption, but roughly speaking, A is large, B is maybe some 0.1 spot shell radius outside. It's a small region. It's roughly the zone outside the black hole. But we don't need to make this very precise to come up with the patterns. Okay, so the first thing to look at is to look at the entanglement entropy of the region A. So remember last time we discussed the so-called page curve, and the page curve told us the following: that if the system was unitary and you looked at the entanglement entropy of A and you subtracted off the contribution you got from the vacuum, then this curve looked like the following. It starts at 0 because in the beginning, when the black hole has just formed, there is nothing in the region A. So the region A looks like the vacuum. So when I write this, I mean entanglement entropy of A minus the vacuum contribution. Okay, so whenever I put this comma and write this omega, it means I subtract off the vacuum contribution. So this contribution is something that starts at 0 because in the beginning, when the black hole is formed, there is no Hawking radiation. Then it rises as the Hawking radiation enters the region A, and that's because the Hawking radiation is thermal to first approximation. And at some point, called the page time, it turns around and it goes down to 0. Okay? And this is called the page time, and it's a time of order n cubed. Okay? And the reason it goes down to 0 is because of unitarity. So the naivest version of unitarity, the simplest version, tells you that at the end, when all the Hawking radiation is in A, the system, the radiation must be pure, and therefore the final entanglement entropy must be 0. But in fact, the page analysis tells you more. It tells you it goes up and then comes down monotonically. So this is the page curve which we discussed at the end of the last lecture, and which is the difference of the entanglement entropy of A minus the entanglement entropy of the vacuum. Order n cubed, it just comes from estimating the rate of evaporation. You see that there's a rate of evaporation which is the loss of energy is given by sigma t to the power 4 into A. Go to the t to the power 4 into A. This is 1 by m to the 4, and this is m squared because the area is. So this is 1 by m squared. If you use this, you find the evaporation time of the black hole is m cubed. The page time is not quite the evaporation time, it's the time when the area has become half of what it was earlier, but that's also order n. There's some numerical constants here that depend on gray body factors and various things, which we're not interested in. It's order n cubed.
Is this based on you actually believe that there should be some large directions to Hawking's calculation at order?
Well, so we'll talk a little bit about what it means about correction. That's what it's about. Okay, are there any other questions about this?
So what does this diagram look like if you don't account for the vacuum contribution?
If you don't account for the vacuum contribution, the whole thing is shifted up by some constant. And it's the vacuum. Okay, so this vacuum contribution is not changing this time. Vacuum contribution is just a constant as the black hole evaporates. You see, it doesn't depend on the stage of A. It's just so if you have to. It's a little tricky because you have to find a way of keeping the boundary of A fixed as the black hole evaporates, and the metric is fluctuating. But provided you're making reference to. So, okay, let me not get into that complication. The vacuum contribution here is just a fixed. It's just a constant. So it's something in the beginning and it's something else in the end. I'll come to the vacuum contribution, but it's just a constant. Does that answer your question, or do you want?
I'm still interested.
In this complication, you see, it's a question of how you define the region A. When you define, you see, when you say you're looking at a certain region of space-time, in general relativity, that's always something complicated, because you have to define that region in a gauge invariant manner. If you're just an ordinary quantum field theory, I can say I'm looking at a region which is 10 meters from the wall. But in general relativity, when the metric itself is fluctuating, that's not something well defined, because if you have a gravitational wave that passes through it, as the black hole evaporates and the metric changes, what you mean by your region A has to be defined carefully. Okay, so that's the complication there. So this is one of the complications I mentioned last time about our inability to define entanglement entropy precisely in a theory of gravity. And this is one of the complications. What is it that you mean by a region in the theory of gravity is itself something that's hard to define in a gauge invariant. Okay. So maybe there is something here about the vacuum contribution. It's worth thinking about more. One would expect that the vacuum contribution is something that stays constant, but it is worth thinking about more about how to define the entanglement entropy in theories of gravity. Okay. Now, let's see what this tells us. You see, if you think about the Hawking radiation process, then the way we think about Hawking radiation is that Hawking radiation is produced inside this horizon, near the horizon, and then it streams out. Okay? So there's some Hawking particle that's produced here, and after a while, this Hawking particle streams out into the region A. Now, if that is the case, then we recognize that if you look at S of A at t plus delta t, okay, then S of A at t plus delta, so let's say I fix some time here. Okay. Let me fix a time here, which is some time t. Let's call this a time t. And let delta t be the light crossing time of the region B. So it's the time it takes for light to cross from here to here. Then you can see that S of A t plus delta t is just SAB at time t. That's because everything that was in B at the time t, after a time t plus delta t has crossed into A. Okay. So you see what the physical process here is that there's some Hawking radiation in the region B, and after a while it crosses into region A. Okay. So the entanglement entropy of A at t plus delta t is the entanglement entropy of A and B together at a time t. Right? Is that clear? So we see that S of A of t plus delta t is S of AB at t. Okay? So now let's fix some time t, and let's only look at entanglement entropies at the time t. So what this tells us is that if t is greater than the page time, okay, then it tells us that, actually I should put, it tells us that S
why can't it be like the things that are Hawking radiation that are moving can't be in direction not perpendicular to the thing but moving close parallel to the horizon or like that?
So Hawking radiation is the outgoing radiation. When you talk about Hawking radiation, the flux that you calculate is the flux that's normal to the horizon. So that's what you mean by Hawking radiation. It's the radiation that's coming out. So this goes back to your question of how close you have to take B to be. So you don't want to take B to be so far that there's too much reflection that's happening. You want to take B to be close enough. Wherever you took B to be, there would be some amount of Hawking radiation that would cross, so this inequality would still hold. Okay, so you see that this fact tells us this. It tells us that if you look at S of AB at time t, minus, subtract off the vacuum contribution everywhere, this is smaller than S of A minus S of A omega. Right? You see that's because of this, because we are now in the downward part of the page curve. So if you're at a time that's greater than the page time, then A plus B together is more pure than just A. Okay, if this is not clear, please stop and ask me, and I'm happy to explain this more. It's not very complicated actually, it's just simple reasoning, so if please stop and ask me. Okay. Secondly, notice that if you look at the region B and C together, if you look at B and C together, then the Hawking calculation tells us, and this is not something we reviewed, but it's true that the Hawking calculation tells us that the near horizon is approximated by the following kind of entangled state. This is the state that you've seen when you write the Minkowski vacuum in terms of Rindler modes, which some of you may have seen. But for those of you who have not seen that, let me just try and explain what this means. What this means is that the near horizon region has entanglement between the region B and the region C. Okay. So one colloquial way of saying this is that when you produce Hawking pairs, you always produce pairs of particles which are entangled with each other. Okay. So the Hawking process always produces particle-antiparticle pairs, and the common way of saying this is that one of them falls into the horizon and the other goes out to infinity. So this popular description you've probably heard, that you always produce pairs of particles out of the vacuum, one of which falls into the black hole and one of which falls out. The more precise way to say that is to say that if this A omega dagger is the creation operator of particles outside the horizon, and this A tilde omega dagger is the creation operator of particles behind the horizon, then this, the Unruh state that we discussed last time, looks approximately to leading order as an entangled state of A omegas and A omega tildes. Okay? And there's some coefficient that goes into the entanglement, but that's not important. The important part is that there is entanglement between B and C. Okay. Because there is entanglement between B and C, this tells us that SBC, BC omega, okay, remember I'm always subtracting off the contributions of the vacuum here, because I'm only talking about the entanglement of the different Hawking pairs with each other. So is this aspect clear to us? This comes from entanglement across the horizon. Okay, this is a consequence of entanglement across the horizon. Okay, is this clear? What this is telling us is simply that if you take B and C together, they together are more pure than just C by itself or just B by itself. In fact, both C and B are thermal to some approximation, but if you take B and C together, then that's more pure than just C or just B itself. That's because these two guys are entangled with each other. Okay, good. So now let's say a little bit more about these vacuum contributions. You see, we have some vacuum contributions. In fact, before we get a real contribution, we have to say a little bit about these vacuum contributions. Okay. So now, I don't have anything. As I said, we don't have a good theory of entanglement for theories of quantum gravity, but we can still say a little bit about what we expect from the vacuum contributions. We do understand entanglement entropy in the vacuum in many theories, including some gauge theories, and we always find that the entanglement entropy in the vacuum of a region is proportional to the boundary, the area of the boundary of the region. Okay. So SR omega is proportional to the area of the boundary of R. Okay? So in a theory of gravity, one would expect, and this is an expectation, it's not a theorem, and this is one of the things which is worth thinking about more in this, is that this is equal to K into A of R, by A of R I mean the area of the boundary of R, divided by L Planck square. So usually what appears here is some ultraviolet cutoff, which in the theory of gravity you might imagine is the Planck length square. And there's some numerical constant which we don't know how to fix. And this is, as I said, an expectation. It's not something that we understand very well, and it's worth trying to understand this better. Okay? But it's a reasonable expectation that the entanglement entropy of a region in the vacuum contribution to the entanglement entropy is proportional to the area of the region. If we accept this, then you find the following identity with these entanglement entropies. You find the following relations for the entanglement entropy. You find that S of C, S of A of omega, is the area of RB. You see, because A has only one boundary, it's this part, so the entanglement entropy of A in the vacuum is just the area of this sphere. See, A is the region outside B, so its boundary is this, this boundary is a sphere, even though I've drawn it in one dimension. So it's actually a sphere at radius RB, and therefore the entanglement entropy contribution of A, this contribution is area of RB. The entanglement contribution of C is the area of RH, is the area of the horizon, plus the area here. Right? So the boundary of C has two boundaries, the horizon and this part. Right? Okay. The entanglement contribution of AB in the vacuum is proportional once again to the area of just the horizon. That's because A and B together form a region which has a boundary only at the horizon. Look at this figure. A and B together form a boundary which has only one boundary, which is the horizon. The other side is of infinity. And the area of SBC, can you see in the back what I'm writing? So I'm writing equal to, I should actually write proportional to everywhere, but it's the same proportionality constant. So so are these identities clear? Now if you just look at this a little bit, you'll find that these entanglement contributions in the vacuum obey the following identity. They obey the following identity, which is that SAB in the vacuum plus SBC in the vacuum is equal to SA in the vacuum plus SC in the vacuum. Okay. If you just add these things up, you can check that this identity is obeyed by these areas. Okay, so there are 4 terms here, you can just add them up and you can check. Because, so you can just, it's just some simple. Okay, but if we combine this identity with these results, okay, then we see actually that we can write down the following identity, which is that SAB plus SBC, okay, is smaller than SA plus SC. Okay. That's because SAB is smaller than SA, okay, as a vacuum contribution, but you can check the vacuum contribution will cancel in this combination. Okay. So SAB is smaller than SA and SBC is smaller than SC. Therefore, SAB plus SBC is smaller than SA plus SC. Okay. In fact, those identities involve the vacuum contribution, but because of this identity, the vacuum contribution cancels. But even though this looks like not something surprising, Samir pointed out that this is actually in contradiction with the strong subadditivity of entropy. So there's a theorem in quantum information that tells us that for 3 distinct Hilbert spaces, if you take any 3 distinct Hilbert spaces, and you look at this kind of combination, there's a theorem which is called the strong subadditivity. Okay. Which tells us that SAB plus SBC is always greater than equal to SA plus SC. So this result that we seem to have derived, this result, is obviously wrong. That's because it's in contradiction with the theorem about the strong subadditivity of entropy, which is that SAB plus SBC is always greater than equal to SA plus SC. And here we have inequality. In fact, you can check how much the inequality is by, and it's not by a small amount. It's not by a small amount because if you start subtracting these sides rather than just writing down inequality, you'll find there's an order 1 difference between the left side and the right side. Okay? So this looks like you have an order 1 contradiction with the theorem in quantum information. Okay? So this is the strong subadditivity of entropy paradox. And the reason for creating this paradox is to try and sharpen the question of whether small corrections can resolve the issue of Hawking radiation. Okay, so your question, yes.
So this seems to be strongly dependent on how we define the vacuum.
How you define, actually it relies on these assumptions. or is that what you're worried about on these things?
On how you actually define the region itself.
Yes, it is important on how you define the region itself. So that's true actually. That's something that's not always realized. That it's important, for example, that A and B together, should have a common boundary. If you try to define A to be some region far away and B to be the region which is in the zone, which is how sometimes it's done in the literature, in fact these inequalities would not work out because of these vacuum contributions. So one of the things that went in here, for example, was that S of AB together was the area of Rh, and that's because A and B share a common boundary. And so if you look at AB together, they have only one boundary, which is the horizon. In fact, if you took A to be some region far away and B to be a region close to it, then SAB would have two boundaries. Okay? It would be the boundary of A plus the boundary of B, and that contribution would overwhelm, because the cutoff here is L Planck squared, the proportionality constant, would overwhelm this contribution you're getting from these inequalities. So in fact, to get a precise contradiction with strong subadditivity, it is important to define the regions correctly and define them to have common boundaries.
But more than that, so for instance, this expression here with SA minus SA vacuum.
Yes.
So the vacuum is defined essentially without the black hole being there at all.
Correct.
But without the black hole being there at all, it's a completely different space-time.
It's a completely, yes.
How do you know where that region A should actually be?
Right, so that's the question we were discussing earlier. How do you know where that region A is actually? One way to try and define this is to try and define it relationally. You see, you could say that let's say you had a boundary in AdS and you're thinking of small black holes in AdS. You can define the region A with relation to the boundary. The boundary is some asymptotic region which is not fixed. And you can say A is a region which is defined, once you fall in 20 proper seconds from the boundary. So you try and define the region A relationally. That gives you a prescription both in the black hole background and apart from the black hole background. It gives you a way of comparing regions which are not in the same background metric. That being said, this is an important question which deserves to be thought about more, and that's because you see, if you had small fluctuations in defining the region A, because this constant of proportionality actually involves L Planck squared, you might worry about precisely defining this region A, and so that's something that needs to be thought about more. So I don't have anything more. I don't think anyone has anything more to say about that. Okay,
so does that relational prescription, does that give this area?
No, this is the second assumption. So there are two assumptions that went into this. One of them was that you could subtract off the vacuum contribution and get something reasonable, which is something, and the second assumption was that the vacuum contribution goes like the area. Both of those are reasonable assumptions, but they've never been made precise. To make them precise, you would have to have a good theory of how to define entanglement in the theory of gravity, which we do not have. So if you had such a theory, it would make these things more precise, but which we don't have, and it's worth recognizing that we don't have them, and this is a possible place to look for more interesting things. Okay. Are there other questions about this? Okay. So you see, this is what's called the strong subadditivity of entropy paradox. Now I'm going to talk about, and as you can see, this sharpens the information paradox because it suggests that you have an order 1 contradiction with some theorem in quantum information, and it's not something that can be so easily resolved with small corrections. Okay. In fact, the strong subadditivity of entropy paradox is closely related to something older. Let me say one more thing before that. So sometimes you will hear this, the strong subadditivity stated in terms of the monogamy of entanglement. So this is related to monogamy of entanglement because what it's telling us is that the page curve tells us that the Hawking radiation in this zone B is entangled with the early Hawking radiation. But the smoothness of the horizon tells us the Hawking radiation outside is entangled with its partner inside. And there's a theorem about monogamy of entanglement which is closely related to this, which tells us that if B is entangled with A, it cannot also be entangled with C. Okay, so entanglement is monogamous. You can't be entangled both with A and with C. Okay, so that's another way of saying this, but the precise paradox you would have to frame in these ways.
This would be like for maximal entanglement.
No. These things are stated in terms of inequalities about entanglement entropies. Okay, the monogamy of entanglement is just a way of saying this in words. There's a precise theorem that goes along with this, which is related to strong subadditivity. Yes?
Something I sort of wonder for often is that you assume that with entanglement that nothing happens to Hawking space inside the black hole. You assume that nothing special happens inside the black hole of these space. Why does something does happen? We don't know the structure inside, so.
Right. So right. It's good. So I think Samir spoke about that. So there's one possible resolution to this paradox. Maybe I can say that at this point. One possible resolution to this paradox is to drop, I think it's fair if I say this, and Samir can correct me if I'm wrong, is to drop this. Is to say that SBC is not close to 0. That in fact you don't have this entanglement across the horizon. So that's one possible resolution to the paradox. That leads you to a situation where quantum corrections correct the interior of the black hole. And that leads you to the picture of either fuzzballs or firewalls, where the classical solution is modified drastically by quantum corrections, and in fact you don't have this entanglement across the horizon. And that's one possible resolution, which I think you already heard about in the first two lectures. Is that a fair statement? Okay. And so I'm going to try and give you another possible resolution, which doesn't rely on this. And I think the thing here is that at least one of the reasons for my discomfort with this solution is it violates effective field theory. So you get a certain solution from effective field theory, which is the collapsing black hole geometry, and then in this collapsing black hole geometry, you would imagine that quantum corrections are small at the horizon scale. But in this proposal, quantum corrections are large at the horizon scale because it breaks the entanglement across the horizon. So then one has to explain how that violation of effective field theory comes about. And there's been some progress which I think you heard about again through this notion of fuzzball complementarity and other ways. But I'm going to give you a different proposal that will preserve effective field theory. Okay. So there are other questions about this. Okay. So let me talk about a closely related paradox, which is the cloning paradox. The cloning paradox is an older paradox, but it's very, very, very similar to this one. So to think of the cloning paradox, you have to think of what are called nice slices. Okay, so I'll just draw the nice slices. Actually, in these notes, which I've written for this lecture, which I'll give today.
I'm not sure when you want to discuss this question, effective field theory. It's always
Always.
By name being effective.
Correct. Yes. This is a large violation of.
What scale?
This is a large violation of effective field theory. You see, you might have imagined that effective field theory is valid up to, up to curvature scale divided by Planck scale. But here, at the horizon, the curvature scale is 1 over the Schwarzschild radius. But the violation is order 1, even if the Schwarzschild radius is much larger. So in the fuzzball and firewall proposals, if you have a black hole which is the size of the galaxy, even though the curvature scale is very small, even then the corrections are order 1, and that the geometry at that point is corrected by order 1. So that is the kind of correction you wouldn't expect in effective field theory.
It's not really Newton's constant.
It is Newton's constant appears through Planck scale. So you would expect that the effective field theory corrections are controlled by curvature, whatever the radius of curvature is, divided by Planck scale. Okay, so you would expect that in effective field theory, corrections to geometry are controlled by L Planck squared divided by R squared, where R is whatever the radius of curvature is. But in this so this is a very small number for large black holes. But in this proposal, the corrections are very large. Okay, so the corrections are order 1, even though this number is very small. That's why it's a violation of effective field theory, and that the corrections are not what you expected. Okay. So to discuss the cloning paradox, I have to discuss these nice slices. In these notes that I've written out, which I'll distribute, I think maybe even at lunch I can give them immediately afterwards to the organizers, and you can see them at lunch. I described how you can construct these nice slices mathematically. It's not very hard. It's a common construction. But let me just draw them for you so you get the picture. So here's a collapsing black hole. So this is a collapsing black hole. This is the surface of the star. This is the horizon. Let me actually. One second. So let me draw the full Penrose diagram, which is correct. So sometimes the Penrose diagram of a black hole which is evaporated is drawn in this way. Let me just correct that. So sometimes the Penrose diagram of an evaporating black hole is drawn in this way. It's meant to show that you form a black hole, but in the end everything evaporates and all the Hawking radiation comes out here. So in the end, this is not a very precise picture, but this is a Penrose diagram which is drawn for an evaporating black hole to show that eventually the black hole always evaporates. So in this kind of a setup, you can draw these things called nice slices. We do this. Okay. We come here, and they go very far up, and they do something like this. Okay. So these nice slices are the slices in red, and they are slices which have the following property. Okay. One, they have small curvature everywhere, and two, they stay away from the singularity everywhere. And the third property, which is something which is an important property, is that in these nice slices, you can draw many types of nice slices. These nice slices have the property that they bend upwards. Capture most of the outgoing Hawking radiation. Okay, it's not difficult to check. You can actually construct slices that satisfy this property. And as I said in the notes, I gave you a more mathematical construction of how to do this. But just think of them schematically rather than trying to go through the equations. Which is that you have these slices that are smooth everywhere. Okay, they have small curvature everywhere. And what these slices do is they kind of hug the horizon. They stay very close to the horizon for a long time. Okay. And therefore, the Hawking radiation that's emitted from here is all captured by these slices. All of it intersects these slices. Okay, remember, the Hawking radiation is emitted from the horizon, and in such a Penrose diagram, it travels parallel to the horizon for a very long time. So these slices have the property that they tend to go up, and then they come out of the horizon at this late time. Okay. And therefore they capture most of the Hawking radiation of the star. So the star evaporated, these nice slices capture the infalling matter, and they also capture the Hawking radiation. Okay, if the slice exited the horizon at this point, it would not do that, right? Because most of the Hawking radiation is emitted at later times. And that's why this slice goes very far in the future and exits the horizon from here and captures most of the Hawking radiation. So once again, you can make it's not hard to construct slices that do this precisely. But it's the picture of what these nice slices do here. This space like such. So the end is space like infinity. Okay. So are there any questions about these nice slices? I don't know if you've seen these nice slices before, but they're a useful construct to discuss black hole evaporation. Okay. Now the thing about these nice slices is that they have small curvature everywhere. By virtue of having small curvature everywhere and staying away from the singularity, you might imagine that you could actually do, ordinary Hamiltonian evolution on these nice slices. Now there is something that is bizarre about these nice slices, and let me say that. And I don't have, once again, I'm going to say I'm going to give you a caveat, and maybe that caveat is worth developing, but I don't know how. And that is the following. Remember, we said that the evaporation time of the black hole outside was order m cubed. So if you have an observer who is living outside the black hole, and as this observer crosses the nice slices, if you have nice slices that foliate the black hole evaporation, then those slices cover, from the point of view outside, a time of order m cubed. Right? Okay. But the amount of proper time that you have inside for any observer is order m. If you have an observer who falls into the horizon and falls into the black hole, this observer crosses, so if you label these nice slices by their time outside the horizon. So let's say this was slice 1, then you had slice 2 and so on. You would have slices of order m cubed if you label them by number of seconds that passed outside the horizon. you would have order m cubed slices, you would require order m cubed slices to foliate the evaporation of the black hole. But the amount of proper time inside the black hole is only order m. So, the ratio, these slices involve a huge ratio as seen by the amount of time outside and as seen by the amount of time inside. So if you try to do Hamiltonian evolution on these nice slices, okay, there would be a huge redshift factor between the way you label these slices in terms of an asymptotic observer at infinity and the amount of and the number of slices that an infalling observer actually crossed in 1 unit of proper time. In fact, the infalling observer in 1 unit of proper time would cross order m by m Planck squared of such slices. Okay, so he would cross a very large number of such slices in 1 unit of his proper time, and that's because of the ratio inside being order m, the ratio outside being order u. The time outside is order m cubed because that's the time of evaporation of the black hole, whereas the time inside is only order m. So now this is it's something which may make you skeptical of doing Hamiltonian evolution on these nice slices, because this is it's what Wheeler used to call many-fingered time, where time pushes forward slowly in some regions of space and faster in some other regions of space, which you've read about in your general relativity courses. This is kind of an extreme version of that, okay, where time pushes forward very slowly inside and very fast outside. Okay. So these nice slices are like many-fingered time, but the amount of time they cover outside is much, much larger than the amount of time they cover inside. Okay, now there's nothing mathematically wrong with that, but it's worth thinking more about this unusual feature of the nice slice. Okay. So they have these 3 features and they also have this feature. Okay, good. So now let me say, leaving this caveat, and as I said, there's nothing mathematically wrong with this, it's worth thinking about more. You might have thought that you could do Hamiltonian evolution on these nice slices. Okay, so you start with the black hole, you start with the star collapses, it intersects these nice slices, and you're doing smooth Hamiltonian evolution. But now notice what has happened, and this is called the cloning paradox. If you think about this nice slice captures a large fraction of the Hawking radiation. Because it captures a large fraction of the Hawking radiation, we know from the argument of Page that it also captures a large amount of the information that was present in the star. But this same nice slice also intersects the infalling star, the collapsing star. So it looks like this information which is present here has also appeared outside on the nice slices. Right? So the information, there's some information here. And the same information is present in the Hawking radiation outside. So it looks like you do evolution on these nice slices which have small corrections, small curvature everywhere. They don't come anywhere close to any singularity. And yet on these nice slices, you've cloned information. You started with some information here, and then that information still exists on the nice slice here, but it's appeared in the second part of the nice slice, which is here. Okay? And that's in violation of a very fundamental property of quantum mechanics, which is linearity. A state cannot evolve to something like this. Okay, this is just wrong. If this happened, then you would violate the uncertainty principle without any difficulty, because this state could have 2 operators that don't commute. On this copy of the state you measure one of them, on this copy you measure the other, and now you've measured both to arbitrary precision. So this is in violation of the linearity of quantum mechanics. You can't clone information. Whenever you do quantum teleportation, you destroy the original qubit. You can't take a qubit and copy it with perfect fidelity. And it looks like the black hole, if you evolve it on these nice slices, is doing this. It's taking the qubits that live on the infalling matter, and it's copying them into the Hawking radiation. So they live on the infalling matter and they've appeared at one more spot. Okay? And that is what's called the cloning paradox. So this is called cloning. and it looks like black holes clone, and that's clearly a paradox. This paradox is actually closely related to the strong subadditivity paradox, in a way I'll make precise in a minute. But you see that this paradox also requires you to make reference to the black hole interior. It's only when you make reference to the interior of the black hole that you get this paradox. It's not something that exists for an observer who's just outside. It's only when you make these nice slices that go both inside and outside and are drawn in a particular way that you get this paradox. Okay. So this is what's called the cloning paradox. Is that clear? Is this? Okay, so are there any questions about the cloning paradox?
So the second thing is like, it's not capturing all of the Hawking.
Yeah, that doesn't matter. First of all, you can make it capture a very large fraction by doing this, and you can't reproduce 90% of the information with perfect fidelity either. You can't reproduce any fraction of the information in a state without destroying the original state. It's not like you can if you had 100 qubits, you could copy 10 of them with perfect fidelity. You can't copy any fraction of them. So the same information shouldn't appear in two states.
There's just like some entropy version of this thing as well. You can write some equation which says that some strong term which means like the equality.
This is actually just violating linearity. I'll tell you why I think it's equivalent, but at this moment it's just violating linearity. It's a statement that you can promote this to a theorem, but it's kind of an obvious statement that you can't, otherwise you would just violate. If the Schrödinger's equation is linear, it doesn't allow you to go from here to here. This just violates linear evolution. I mean, there's a no cloning theorem, but that's an unnecessarily fancy name for this, which is just linearity. Okay. Any questions? Other questions about this? Okay, good. So now I'm going to try and explain why these two are related, and also give you, in the last 10 minutes or so, give you a notion of what I think the resolution to these is. Once again, you can resolve this by basically saying that the interior doesn't exist in this form. So if you said the interior doesn't exist in this form, or there was a fuzzball or a firewall inside, then this paradox would not appear, because these nice slices would not see the star inside. All the information would physically come out, it would not exist in this part of space-time. Okay, but I'm going to give you a different resolution which will obey effective field theory, and the different resolution is as follows. And in a sense, the cloning paradox tells us gives us one possible resolution, which is kind of staring us in the face here, which tells us that, you see, what if it's not linearity that is lost, but locality? So this is an interesting idea, which I'll make very precise in the next lecture, but let me just introduce the idea here. What if it's not linearity that is lost here, but locality? You see, because we think of the degrees of freedom on one part of the nice slice as being separate from the degrees of freedom on the other part of the nice slice. But what is it that Hawking radiation is really doing? What Hawking radiation is really doing is that it's taking the information here and it's scrambling it into quanta of Hawking radiation. It's scrambling it into quanta of Hawking radiation, so the information that exists here is not easily accessible by measuring simple observables on a nice slice here. It's accessible only by measuring, complicated combinations of observables by looking at delicate quantum correlations in the Hawking quanta that are emitted here. So this information, which is available easily to an infalling observer here, it's just available by going and measuring simple effective field theory degrees of freedom, is available here only by measuring complicated combinations of simple effective field theory degrees of freedom here. Okay. What if what is violated is not linearity but locality in a theory of gravity? More precisely, what if we were to identify, and this is an idea that we call black hole complementarity, what if one identifies, some field operator inside the black hole horizon as a complicated polynomial of field operators outside the horizon? How complicated? A polynomial involving order S. Okay. If one makes this identification, and I'll tell you what you have to be careful about in making this identification. then you see you would not have a cloning paradox. You would not have a cloning paradox because what is happening here is that the nice slices are deceptive in that they suggest that this part of space is the degrees of freedom here are different from the degrees of freedom here. So it looks like you've cloned the degrees of freedom. But if in fact you identify the degrees of freedom here with the degrees of freedom here, then you have not cloned the degrees of freedom. It's just that what you thought that the information was here and here, but this is in fact the same information. In that if you made a complicated enough observation here, it would also affect the information here. Okay. So the idea of black hole complementarity is that what is violated is not linearity but locality. In a sense, holography tells us that something like this happens. It tells us that we have some bulk space-time, but you have a holographic description of the bulk space-time, so that it looks like degrees of freedom near the boundary. All the information exists at some point near the boundary, but some part of that information is also accessible by doing some measurement in the bulk. Okay? So in a sense, complementarity is natural from the point of view of holography, and the idea is that you identify the degrees of freedom inside the black hole with a complicated polynomial of degrees of freedom outside the black hole. If you do that, then you see you've resolved the cloning paradox, because there's no cloning happening. It's the same information that's present here and here. But what you have lost is locality. What you've lost is exact locality, because now this degree of freedom is not, is not distinct from these degrees of freedom outside the black hole. Okay? Okay. Now you have to be very careful when you do this. First of all, I think, and very legitimately, you should ask me to make this precise, because this is an idea, but okay, why would you believe this? Why would you believe that such an identification existed? So in the third lecture, I'm going to give you an example of where, let me put here tilde, because for now I certainly haven't done enough to justify writing it as an equality. So in the third lecture, I'm going to make this precise and give you a formula where I will be able to write equal to. Okay, so that's later this evening. But let me just say a few consistency checks that you should obviously demand of a formula of this kind. First, obviously the world that we see around us is approximately local. So if you write down a formula of this kind, it's very important that one consistency check that you have is that, if you look at 2 points inside the black hole, so imagine some infalling observer who measures this commutator and measure some low point correlation function inside the black hole. So maybe he measures a 4-point correlation function. Okay. So you have an infalling observer who measures the commutator, which you can measure by doing some retarded experiment, and measures the 4-point correlation function inside the black hole. This person should certainly not see a violation of locality here. Also, if you had some observer outside, it should not be easy to send messages from outside to inside by means of a relation of this kind. Okay. So this commutator should vanish to excellent approximation in low point correlators. Okay. So the moment you identify degrees of freedom on one part of a space-like slice with degrees of freedom on the other part, you've also given up an exactly zero commutator. That's because 2 degrees of freedom are the same, and so clearly they don't commute exactly. If you do that, it must still nevertheless be true that approximately within low point correlators these degrees of freedom commute, and that's necessary if you want to preserve consistency with approximate locality. Okay? So that's a very important check, and I'll point out how the construction will give you later today will obey this check. Okay. Let me also say, so this is an important check which you need to ensure, which is the first thing that you would like to ensure for any such relation. So this relation violates locality, but it violates locality in a clever way. It has to violate locality in a clever way, in that these violations of locality are not manifest within effective field theory. So there are some non-perturbative violations of locality, but they're not manifest within effective field theory. If they were manifest within effective field theory, we would again be giving up effective field theory. So there's no point of writing down a construction of this kind if it violates effective field theory. So it's important that any such relation you write down will obey this, and which it will. Okay, let me say this also resolves the strong subadditivity paradox in the following way. It resolves the strong subadditivity paradox. Remember, and it's still on the board fortunately, the strong subadditivity paradox said the following. if you have a direct product of 3 Hilbert spaces, then the entanglement entropy of the density matrices obeys this relation. Okay. But if the Hilbert space, if you have a relation of this kind, then the Hilbert space does not factorize into the Hilbert space inside and the Hilbert space outside. Okay. If this C is not a factored, if it's not a direct product, if the Hilbert space of the black hole is not a direct product that factorizes into inside and outside, then you don't have a strong subadditivity relation. Okay. So if Hilbert space does not factorize, then there's no contradiction with strong subadditivity. Strong subadditivity effect. So the way a complementarity would resolve the strong subadditivity paradox would be by stating that the Hilbert space doesn't factorize into inside and outside, and therefore you shouldn't be writing down the relation of this kind. That's because C, in a sense, is a scrambled version of A. So that's the basic idea. And as I said, this is certainly it's in a sense a remarkable proposal, and so you should certainly ask me for more evidence, and I'll try and explain to you how something like this holds in the third lecture, just in empty AdS. So just to give you a preview, what I'll try and do is I'll just look at empty AdS CFT, which doesn't even have black holes, and try and argue that in empty AdS, you have a relation where you can write an operator in the middle of AdS as a polynomial of operators that are uniformly spatially separated from that operator. Okay, and so this is a relation, if it holds, shouldn't hold only in the black hole background, because after all, there's nothing special about the black hole. On these nice slices, the presence of the horizon is some global property, and if you have a relation of this kind, it shouldn't depend on the existence of a black hole, and indeed. Okay, so I'm mostly done. Let me just review very quickly in the last 1 or 2 minutes I have, I think. Okay. So as I said, just to say what we've done so far. I said that there's a naive information paradox. The naive information paradox is the statement that Hawking radiation is thermal. That paradox is easy to resolve using small corrections. You can refine the information paradox by making reference to the black hole interior. A refinement of the information paradox goes through the strong subadditivity of entropy, which says that if you look at some region close to the black hole outside, this region is entangled with the inside, but it's also entangled with the Hawking radiation far away, and that violates the monogamy of entanglement. Another refinement goes through the cloning paradox, that's older, but in a sense less precise, but older, and that says that if you draw these nice slices in an evaporating black hole background, these nice slices intersect the infalling matter, they also intersect the outgoing Hawking radiation, and as a result it looks like you've cloned information from the infalling matter to the outgoing Hawking radiation, and that's in violation with linearity. One proposal, of course, is to say that the interior doesn't exist in this form, but if you'd like the interior to exist in this form and like to preserve the classical solution because of effective field theory, then another proposal that resolves these paradoxes is by means of complementarity, which says you should identify degrees of freedom on this slice, but you have to identify these degrees of freedom in a clever way so as to avoid contradicting everyday experiments which do show locality. So the claim is that there is some very complicated polynomial of operators outside which is the same as the operator inside. So this is an identification not of expectation values in a state, it's an identification of operators, and it's an identification that's clever enough that it makes sure that the commutator and low point correlators vanishes. If such an identification exists, then the Hilbert space of the inside and the outside does not factorize. As a result, you don't have any strong subadditivity of entropy relation, and so it also resolves a strong subadditivity paradox. Okay, so I'll stop there, and in the last lecture I'll try and convert this to an equality in a specific example.
Right, so we have time for a few questions.
Can you say again, why is this no longer like 0 exactly? What stops?
Why is it? It's clearly not 0 exactly, because if you had a relation of this kind, and at this point, you would also have a relation which would tell you the canonical momentum at this point for some other polynomial, right, on things outside. And you see, and the canonical momentum has an order 1 commutator with So now you take this P prime, which is something which is only operators outside, and commute it with this. It has to give you a commutator of order 1. So, if you identify 2 degrees of freedom, if you're going to say one operator in a Hilbert space, one matrix is a product or a polynomial of other matrices. So let's say I give you 2 sets of matrices. Okay, they're just sets, they're not. And I say one matrix is actually can be identified with a complicated enough polynomial. Then clearly the commutator between them is not 0. Let's give you one example that yes.
So you are taking like both are phi ins, right?
Okay, good. So such a relation, it's both are phi ins. I could make one of them phi out. If such a relation holds, it's not a relation that will hold. Let me make one of them phi out. It's not a. This is the statement that you can't send messages from inside to outside. But if such a relation holds, it's a relation that might hold at many points on a nice slice. All I was trying to say was if you identify degrees of freedom at one point with some other point, you have to make sure that it's consistent with locality. This is also true, by the way. It's also true that x in 1 and x in 2 has to be 0, has to be close to 0. And in fact, this will also be violated because the moment you do something like this, you will not be able to preserve exact locality anywhere, either only in the nice slice or only inside and outside. One example of this, as Antal was pointing out to me, was just the fact that if you take a matrix, there are characteristic relations for the matrix that tell you that some very complicated polynomial in the matrix, which is of order, of size, of order the size of the matrix itself, can be identified with some low order polynomial. So you might have thought that m to the power n plus 1 was independent of m, but in fact that's not the case.
If you go above the size of
if you go above the size of the matrix itself. Okay? So so this is a relation that's of that kind. It's saying that you have a very complicated polynomial, which is identified with some low order polynomial. This doesn't violate the fact that approximately, low order polynomials all look independent. But if you look very closely, you see there's some relation between these degrees of freedom.
And the thing that you need to resolve this thing is not just that, that there should be non-locality between the things which are the part of this slice. The degrees of freedom living on the part inside the horizon and outside the horizon are non-locally connected. But they can have non-zero things within.
It's not something you need to resolve the paradox, but I'll try and write down a relation, and you'll see the moment you write down the relation, you will not be able to define exactly local operators even inside. But it's not something you need to resolve the paradox. What you need to resolve the paradox clearly is that the degrees of freedom inside are written in terms of degrees of freedom outside. But there should okay. So and what we'll see is that. But in general, there's a problem with defining exactly local operators in gravity anyway, which is something which I'll emphasize, which is where this comes from. I mean, I don't want to emphasize too much on the fact that they were both in. If you like, just think of the in and out, which is what you need. I wrote both in, but just think of in and out because that's the statement you can't send messages from inside to outside. So that's the more important part. And that's the part which is relevant for this. Okay, so.
Any further questions? No? Let's try to speak again.